Next up, we have Thomas Epps from the University of Delaware. I think if you can, Thomas, if you can go ahead and turn your mic and camera on and your screen. Yeah, fantastic. It's a real pleasure to have Thomas here. Is a long-term personal friend, and it's fantastic to have him virtually, at least, at Northwestern with us today. Thomas is the Thomas and Kipp Gutshall Professor of Chemical and Biomolecular Engineering at the University of Delaware. He has an appointment in Material Science and Engineering and an affiliated appointment in Biomedical Engineering. He's the director of the Center for Research in Soft Matter and Polymers, and is also the director of a new MRSEC at the University of Delaware, and co-director of a new EFRC as well. He's going to be very busy. His research interests include nanostructures assembly for targeted drug delivery and gene therapy. He makes polymeric materials for various applications of all kinds, including bioseparation, ion conduction membranes, nanostructured soft materials for bio-based feedstocks, which he'll talk about today, I believe, and a whole range of other applications in nanotemplating and some interesting uses in polymer metal organic framework composites. Thomas has received many awards, and we won't list them all today, but these include the John H. Dillon Medal, the Owens Corning Early Career Award. He's a Kavli Fellow of the National Academy of Sciences, is a winner of the PCASE Award and an NSF Career, among many others, as I said. He was elected a Fellow of the American Physical Society in 2017, and is a Fellow of the Royal Society of Chemistry as of 2018. He's a member of the Department of Energy Basic Sciences Advisory Committee and is an associate editor of Science Advances. I'm going to hand it over to you, Thomas, and turn my mic off. But welcome, and thank you for coming today.
Thank you very much, Nathan, for the kind introduction and also for the invitation. It's very much a pleasure to be here. So as was mentioned, what I'm going to talk about today is a little bit of our work in biomass and trying to actually valorize biomass and convert it into some more useful materials. And so we're really focused in this particular talk on some of the things that we're doing with lignin, and a lot of this is actually part of an NSF growing convergence research program that we have at UD. So I'm going to talk about two parts. The first part is really just looking at how we can depolymerize natural products and then produce nanostructured and self-assembling materials. I'll go through some model studies and tell you a little bit about why we do these model studies to help us develop structure-property relationships, and then how we can apply those relationships to real materials and really begin to get a good understanding of feedstock to materials and performance. In the second part of the talk, sort of near the end, what I'll talk about is some of the replacements that we're envisioning for BPA. And we're looking at using bio-based materials in particular to do performance enhancements while also reducing the environmental impacts of some of our resins. So as was mentioned, what this really revolves around is sort of looking at things from a materials lifecycle management. And so one of the things, as many of you are aware, are things like ocean plastics, other sorts of systems where we really want to control not only the source of our polymeric or plastic materials, but what's essentially done with them in the longer term. And so as part of our materials lifecycle management, which is again a growing convergence research program, we're really focused on everything from the engineering aspects, and I'll talk a little bit about those, the math and physical science aspects, so how we design our polymers, as well as then integrating them into the geosciences aspect. So where do our feedstocks come from? How do feedstock environments influence the properties of our polymers? And then integrating that with some toxicity studies that I'll mention today, as well as some other studies that are currently ongoing. So really, in a nutshell, kind of what we want to do is we want to do the following. So if I take a tree, I can look at basically taking the cellulose and hemicellulose, turning it into paper, and then also producing chemicals, fuels, and some plastics. Now, one of the major components of that tree is also the lignin. And typically that's burned in an incinerator or something of that sort. And if you look at the amount of lignin that's burned every year, it's approximately the amount that would be necessary to build 250 Empire State Buildings a year. And so we want to say, can we take that and actually use it to do other things? So can we build performance advantage materials like new tennis shoes, dental resins, adhesives, and other sorts of materials? And I'll give you a little bit of a flavor of a few of those as we go along. So when we're thinking about this, we can say, okay, we're looking at a bio-based material. We're looking at a material that's coming from, in this case, trees or other feedstocks. And so we want to be able to address a series of different criteria when we're thinking about using these materials. So in particular, we want to have a source that's abundant. We want to have relatively simple and straightforward, or at least scalable chemistries. We want to look at chemical toxicity. And so even though we're using natural products, we still need to be concerned about the toxicity of our materials. Two of the main things that I'll focus on, or one in particular, is the properties of the material. And I'll also talk a little bit about costs and how that allows us to sort of optimize and think about the different types of studies that we want to do. I will mention a couple things. We want to make polymers. And in this particular case, we actually want to be able to have control over our polymer systems. So we want to use a bio-based natural feedstock. We want to do it at low cost, minimal separations, but be able to make nanostructured materials such as bio-based block copolymers. So as I mentioned, the first thing I'm going to tell you about is a little bit about bio-based and self-assembling materials. And just to mention some of our targets, we're really interested in block copolymers that form things like thermoplastic elastomers. So one common one that many people might be familiar with is polystyrene polyisoprene, so a styrene isoprene styrene type block copolymer. And you can think of things like rubber bands, car tires, gaskets and O-rings, and other sorts of materials. Now we're interested in trying to make bio-based analogs of these materials. In this particular talk, I'm going to focus more on the red, the components in red, so the polystyrene. We're also doing a lot of work in terms of polyisoprene replacements, but I won't focus on that today. But in particular, one of the things that I want to mention is that there's some good news and bad news here. So one of the pieces of good news is that when we think about bio-based polymers, they're materials such as polylactide, which are or have been commercially viable materials and shown sort of some of that promise that you can have from bio-based systems. However, if we're thinking about things like polystyrene replacements, you can see that polylactide in particular falls short when I start thinking about glass transition temperatures or use temperatures of these materials. I can also switch to something like a polyalpha-methylene gamma-butyrolactone type polymer. That's again quite nice, and you can see in this particular case, I get a glass transition temperature. I can think of that as a use temperature, and I'll talk about that in a minute, of about 195 degrees. So that sounds quite promising, but what that also means is that I have to heat this material up to well above 200 degrees in order to thermally process that, which is very energy intensive. If I look at this in another way, there's another problem. So if I start thinking about polystyrene, and not saying we're going to replace all of this with our bio-based materials, but you're looking at something of the order of 20-ish million tons a year in terms of production. So if we're looking at our existing bio-based feedstocks, we have things like polylactide. You can see I've zoomed in on the arrow now, and you can see that there's the opportunity to compete with food supplies, and that's not something we'd like to do. If we think about the alpha-methylene gamma-butyrolactone, takes intensive farming and deforestation. I didn't necessarily talk about yield yet, but one of the key things when I think about getting that monomer for the lactone-based polymer, I get that at 1 weight % yield from tulips. And so basically what you're looking at is then to produce 20 million tons of polystyrene, I need to start thinking about growing 2 billion tons of tulips, right? So what we want to look at is there another feedstock that we can use that doesn't compete with food supplies and doesn't necessarily involve intense farming and deforestation? And by the way, hopefully our mass yields can be quite a bit higher. So one of the molecules that we chose, or one of the materials we chose to work with, was lignin as a feedstock. And there are a couple nice reasons for doing this. The first thing is, if I think about lignin as a feedstock, I can take a pulp and paper mill or a biorefinery, and those facilities are very good at using the cellulose and hemicellulose components of the lignin, or of the tree, as I've already described. And again, typically what's done with that lignin, now you can see it's about 15 to 25%, is basically burned for energy recovery, or subjected to some other form of pyrolysis, or worse yet, just thrown into the landfill. And when I think about a biorefinery and economic viability or feasibility, you can think about it as basically you take your feedstock and you're immediately told that you're going to take 25% of it by weight and throw it away, and you have to figure out how to be viable with the other 75%. So the question is, can we actually become viable with that 25? Now, one of our goals is actually, can we make that 15 to 25% more valuable than that other 75%? Not sure if I'll convince you that we can do that, but I'll certainly try to do that as part of this talk. So when we think about it, right now, as I mentioned, only 2% of that lignin is used as a chemical feedstock. The rest is thrown away. But one of the nice things is, if we can find good ways to do that depolymerization, we can actually end up with molecules such as methoxyphenols, phenols, and dimethoxyphenols that look fairly similar, if I squint, to something like styrene in terms of having an aromatic character. Obviously, we would need to figure out how to introduce polymerizable handles in order to make our controlled polymer systems. One of the other interesting things that I'll come back to a bit later is, depending on whether we have softwood, we can get methoxyphenols and phenols, or hardwoods, we can get dimethoxyphenols, phenols, and then also some methoxyphenols at all. As we go through, I'll explain why that's important, but one of the key things just to think about is, if I take a softwood, an example would be pine. You can imagine a pine tree swaying in the wind, and you can think about the properties that a polymer from that tree might have, versus an oak tree, which is quite hard and stable in the wind. And you can think about the properties that a polymer produced from an oak tree might have as well. Now, as I mentioned, we want to do block copolymers. One of the reasons, if we think about a block copolymer, I don't need to do too much of an introduction for this audience, but I'll just mention a couple key features. So we want to be able to take two homopolymers, chemically connect them together. This is not the standard way to make a block copolymer, but it's certainly in the realm of synthetic feasibility these days. But the key point is that we can get nanostructured domains, and we can use those nanostructured domains and take advantage of that self-assembly to basically imbue the polymeric materials with some nice properties, including things like tackiness, as I'll talk about a bit later, some of the peel forces, and the ability to withstand stress, keep their shape, and those sorts of things. Well, now, one of the things that's obviously important if we want to make our block copolymers is that we'd like to be able to use different types of chain growth polymerizations to do this. And so that gives us control over molecular weight, obviously volume fraction, gives us homogeneous chain configurations, and in many cases can give us relatively narrow chain length distributions. And so the way we can think about this is basically through the chain growth. I can have monomer A that I'm adding to a chain, monomer B to make block B, block C, and so on. And so we can make various types of block copolymers and think about using them for different applications. In this particular case, I'm just going to mention one particular example, which is thermoplastic elastomers, where instead of just AB, we want ABA block copolymers. The reason for that, as you can hopefully see here, is that I can start having glassy regions, in this case made of a styrene or polystyrene mimic, that I can stretch and release, and think of something like my rubber band, where I can stretch it, release it, and goes back to its original shape. And part of that is because I can take advantage of some of the self-assembly that I get from having that block copolymer chain architecture. Now, one of the things that I can think about, again, I'm going to focus on the red here in the talk, is that if we have, say, a polystyrene, relatively abundant as we talked about, glass transition temperature right at about 100 degrees, and that's right at about the use temperature for many polystyrene-based materials. For those of you who are not quite familiar with what that means, think about your styrofoam cup and adding boiling water to it. That's about the temperature where that cup becomes quite soft, and that softening temperature is very close to a glass transition temperature for the material. Now, when we think about degradation temperature greater than 200 degrees, why is that important? Because in many cases, if we want to melt process our material, we want to have a good window, in this case 100 degrees, between that glass transition temperature where it becomes soft and has more of an ability to flow, and that degradation temperature above which I can no longer process that material. Now, two advantages that we hopefully have with these bio-based materials is we're not petroleum-based, and our monomer, as opposed to styrene, is not going to be toxic or volatile. And again, as I mentioned, just some of the applications, so shoe soles, car tires, rubber bands, and even different types of packaging, etc. And so I don't need to focus too much on this, but I will mention that we can do both free radical polymerization, and there's reasons that we might do that. But then in this particular talk, what I'm going to focus on is some of our work on raft. And one of the reasons for that is because, as you can imagine with bio-based materials, we've got different functional groups in our polymers or in our soup, and we want to be able to have a controlled polymerization method that's going to be sort of amenable to having different functional groups like aldehydes, hydroxyl groups, and other sorts of things. So one of the things I'll mention now, and I'll also come back to a little bit later, is this effort is really a collaborative effort with our Center for Catalytic Science and Technology. One of the reasons that I mention this is because I'm not really going to do them justice in this talk, but basically say that there's a lot of work that goes into taking that wood and through this arrow, then starting to turn it into some of the small molecules that are shown here in the green box. For now, I'm going to focus on model studies to start out with. And basically what I'm showing here is some model compounds that I can get from catalytic depolymerization of lignin. Now what we can do, we can take that, we can do various types of one-step functionalizations, and put, say, for example, a methacrylate or acrylate group on that phenolic hydroxyl. Why do we want to do that? Well, because now we can take something that's not amenable to a chain growth polymerization and put a methacrylate group on that, which is readily amenable to that type of process. So in this particular case, what I'll show you is first how we can take each one of these individual components, make a homopolymer, develop some structure property relationships, and then use that to not only predict some of the properties of mixtures, but then apply that to some real materials that I'll talk about in a few minutes. So in this particular case, we had several criteria that we wanted to hit. As I mentioned earlier, one of the key things was, do these materials have glass transition temperatures around or greater than 100 degrees Celsius? So just showing some DSC data on the left, the curves are shifted vertically for clarity. But the key point is basically in the right-hand chart in the rightmost column. So the key thing is that all of these materials as homopolymers have glass transition temperatures near or above 100 degrees Celsius. So this is quite nice because not only do they match polystyrene, but now you can imagine if I take this material here, PCM, so polycreosol methacrylate, if I were to make my quote unquote styrofoam-like cup out of that material, I could even think about boiling my water now in my cup as opposed to boiling it in a tea kettle and then transferring it over. So there's a lot of application where being able to get just above 100 degrees Celsius in glass transition temperature is quite useful. Now we can take these materials and also look at thermal stability. So we can do thermogravimetric analysis. I will mention that in our case, we do it in air. as opposed to nitrogen. One of the reasons that we do this in air is because it more closely mimics what might be done in a commercial process. So in this particular case, the key point is just showing some curves here, but the key point is that the onsets of degradation, as you can see, are all between about 250 and 300 degrees Celsius. So basically what that means is that even for the worst performing material here, which is the ethyl version of the methacrylate, that we basically have about 150 degree glass transition to degradation temperature window for these materials. So now we can take them, and I'm putting this slide up to illustrate basically two things. So one of the first things is that all that I've shown so far is basically our monomethoxy materials. And so these are basically the monomeric units that can come from softwood such as pine trees as one particular example. And so what you can see here is that basically what happens is I got a methoxy unit on this side and then a hydrogen here. And I have glass transition temperatures about 100 to 130. Now, if we move to the hardwood, so something like oak, and now I have 2,6 in this case, so a dimethoxy substituted material, then what I can see, and notice the break here in the y-axis, is that I now get glass transition temperatures above 200 degrees Celsius. And so that's quite nice for two reasons. One of them is that you can imagine that I can co-polymerize these different types of monomers because I have methacrylate functionalities on both. But the second thing is that I can actually start making polymers with glass transition temperatures above 200 degrees from material that I would otherwise burn or throw away in a landfill. And so what can we do with this? So one of the nice things is that we can actually look at polymerization rates for these materials. So I'm putting this here. And part of the reason that I want to show this is because we can polymerize essentially homopolymers, or we can take bio-oil methacrylates, which is basically mixing all of those homopolymers together and doing a polymerization and essentially monitoring the kinetics. But the key point here is that no matter whether I have a single methoxy or two methoxys, the polymerization rate is approximately the same. So what that means is that now we can actually think about using things like the Fox equation and Flory-Fox equation, for example, to predict the properties of our materials as we have basically a statistical or random polymerization in a single block. And so here's just one example of how we were able to do that. And I'm going to spend just a minute on this slide kind of walking you through a little bit about what happened here. So one of the first things is that we were able to get this depolymerization data courtesy of Mike Klein, who basically did a computational analysis of Kraft pine lignin depolymerization, in this case through pyrolysis. This is the only slide where I'll mention pyrolysis in terms of what we were doing. Anyhow, what he was able to do is actually through his computational modeling of the kinetics actually predict what would happen in terms of distributions of monomers in column A versus B, where the only thing that's different is the pyrolysis temperature of 550 degrees versus 600 degrees. Then what we are able to do is we're actually able to use the Fox equation, shown in the top right of the screen, to predict what the glass transition temperature of a mixture of those components would be if we polymerized it based on the homopolymer data that we'd gotten previously. So we're able to do that, and if you look at the left-hand side, what you can see is the open triangles, and this is just two of many examples, where you have the predicted data, glass transition temperature data. Then what we were able to do in collaboration with Dion Vlachos's group is actually do the pyrolysis, clean up, make the block or make the homopolymer in this particular case, measure the glass transition temperatures at the two pyrolysis conditions, and actually we're able to get the solid data. And so what you can see here is that the data differ by about 1 degree, give or take, between the predictions and the measured data. This is one of the better samples. I will say that some of our worst data is off by about 5 to 6 degrees. So we're still very good and in the ballpark of having some good predictability. And I'll show you how we can use that a little bit later on. So now can we chain extend and make block copolymers? We've done a variety of different things with this. So in one particular case, we can take this vanillin, which we can methacrylate. So vanillin methacrylate, we started here because vanillin's actually a commercially viable molecule that I can get from lignin depolymerization. It's used primarily, as you know, in flavoring. So most of your vanilla flavoring is from vanillin, which is either petroleum-based or from biomass. But we can take that and we can actually polymerize it, in this case, as a block copolymer with lauryl methacrylate, which we can get from used cooking oil. We actually got this from the University of Delaware one of the dining facilities. And we can make that block copolymer, and one of the nice things about it is shown in the electron microscopy images here. So we have TEM, and we basically, as you can see with after staining, we can essentially see that we have dark regions of spheres in a light matrix. And that's quite nice because that's actually that very nice thermoplastic elastomer type structure that we would want. And then when we take that material, and I won't focus too much on this now as I have another example later on, but this has a nice tackiness to it, which has a consistency that's very similar to the back of sticky notes. And we actually have a company that's licensed this material and is interested in using it. I will mention that the color from this is the chain transfer agent, which is pink. We can actually burn that off at about 85 degrees Celsius and then give a nice clear material. Just didn't give as good a picture, so we left it in there for artistic license here. Now, that's nice that we can do that with our model materials, or basically materials where we've cleaned them up very nicely. But what we wanted to do is see, can we take these materials and make them directly from biomass using real lignin? And in this particular case, what I'm going to do is I'm going to tell a brief little story where we use biomass, in this case poplar wood, depolymerized that poplar wood, functionalized it, polymerized it, and then we're able to fabricate some pressure sensitive adhesives. And I'll show you some data to indicate the potential commercial competitiveness of these materials. So one of the things I'll mention is that poplar wood looked basically like sort of brown sawdust. We actually used a $20 or about $20 to $40 burr grinder, old burr grinder, and ground it up so that we could do the depolymerization. Did a catalytic depolymerization. If in the Q&A, happy to talk a little bit about the work we've been doing there on optimizing that. Functionalized it, made the block copolymer, and then tested. So one of the nice things about doing catalytic depolymerization as opposed to, say, pyrolysis is that when we do that catalytic depolymerization, we can do it at much lower temperatures and in some instances even much lower pressures. So the nice part about that is that we can get more selective bond cleavage in the lignin. So we can really cleave things like the beta O4 linkages, for those of you who are familiar with that. And that leads to a relatively small distribution of products when we look at the gas chromatogram. Now, hopefully one of the things that you can still see here is that our next step is functionalization. We want to have a linear polymer, and you'll notice, for example, these dihydroxyl species here and here. So the nice part is the only separation that we had to do was a liquid-liquid extraction with a hexane water, a little bit of methanol mixture, and we're actually able to end up with a gas chromatogram that looks like this, that only has these monofunctional species that then we can functionalize to make our chain growth polymer. So no column chromatography or anything for these bio-based feedstocks. So we can take them, we can actually, if we want to, extract the various components. We had these two major components, so the 4-propyl glycol, so 1-methoxy the 4-propyl syringol, so in this case 2 methoxys. We could actually polymerize, or in this case do acrylate functionality instead of methacrylate. Polymerize, for example, homopolymers if we extracted some just to get an understanding of what the glass transition temperatures would be. But I will say for going forward, we actually just used the mixtures because they had the exact properties that we needed. So we can take that block copolymer, again, made from the mixture of biomass. I'm not showing the GPC data, but just suffice to say, we were able to make that block copolymer. We could show that we had chain extension to make this nice, we called it SABSA tri-block copolymer. And what I'm doing here, and you can see faintly the faint ring, there's a little bit less electron density contrast in this material, this bio-based material, than I see in the commercial base, which is a methyl methacrylate, butyl acrylate, methyl methacrylate tri-block copolymer. But the point of showing this is that we actually have about the same domain spacing, we have the same composition. I'll show it here. We have the same glass transition temperature type behavior. And from TEM, which is not shown, we actually have the same spherical morphology. So we really think that we're making an apples to apples comparison to what I'm going to show next. So what we can do is we can take these materials, we can actually cast them onto, say, a polyethylene backing and do some ASTM standard tests. And so one that I'll show you two. So one in particular is a peel test, where we're able to take our materials, put them on either a glass slide in this particular case or stainless steel, and do a 180-degree peel test. Before I move to the data, I do want to focus on one particular thing, which it might be hard to see here, but if you actually see our tape, it's pretty clear. And so the nice part about this material is that liquid-liquid extraction and that depolymerization, catalytic depolymerization allowed us to really get rid of the brown color and again produce a nice, clear, aesthetically pleasing material if I start thinking about tapes and other applications where I don't want a material that's necessarily black or brown. And so one of the things that we can do then is we can take it, we can do that peel force, 180-degree peel force study. You can look at our material, our block copolymer. You can compare it to that base MBM. So you might say, well, what is this comparison? But basically what I do is I take a base like MBM, I add a bunch of tackifier, other additives, and that's how I get things like my Scotch tape and my Fisher brand labeling tape. I will mention that our bio-based material has no tackifiers, no additives, pure block copolymer, and we believe in some work that I'm not going to show here today, but we get that adhesion and that additional surface energy or that surface energy enhancement from having the methoxy groups on these materials which promote adhesion to things like the glass slides, etc. But the key point here is that we're right in the ballpark of Scotch tape and things like Fisher brand labeling tape. We can do other tests as well. So just a loop tack test where we take our sample, basically put it down on a slide or a stainless steel, a piece of stainless steel, and then pull it off and measure the peel force. And you can see the same sort of thing. Now, one of the nice things is that we can actually add additives such as tackifiers, for example, to move this up in particular and match things like Fisher brand labeling tape, or even adjust things to Scotch Magic tape, for example. We asked 3M, for example, what their exact additives were. They, of course, wouldn't tell us, but we were able to make some good guesses and we're able to get materials that fall right in line with that. So the other things that we can do are quite nice is that, not only can we use these materials for things like adhesives, we can also use these bio-based materials, for example, as replacements for polystyrene or alternatives for polystyrene, where I want a material that is potentially just as cheap, but has a higher glass transition temperature. So you can imagine, again, now using, say, this guaiacyl methacrylate, we can go up to about 120 degrees Celsius, a syringol methacrylate, TGs above 200, or mixtures of other lignin methacrylates and acrylates that allow us to really tune in that range between, say, about 50 degrees and 170 degrees. And one of the nice points is that you can say we lose a little bit in modulus, but I would say that depending on, for many applications, this 200 to 300 megapascal range for these materials at 100 or at 115 degrees is going to be quite useful for many applications. Now, one of the nice things that we can do is we can actually predict thermal properties. And so this is quite useful because, as you can imagine, when I switch from one bio-based feedstock to a next, the composition of the lignin might be different. If I switch from growing it in Iowa versus growing it in North Carolina, the soil might be different, and so I can get a different type of feedstock. So one of the things that's quite nice here is that what we can do is that if we have information on the composition, which in these particular cases that I'm showing in the table, we can actually get this data from basically the renewable feedstock library at Idaho National Lab. But the key point is, if we know the composition of different guaiacols, phenols, and syringols, because we've got that glass transition temperature data, and because we also have basically statistical or random copolymerizations or heteropolymerizations, we can actually predict what glass transition temperatures we would get if we made polymers from switchgrass, poplar wood, corn stover, used coffee grounds, other sorts of material, peanut shells, for example, and whether it's methacrylated or acrylated, and all of these values are within 5 degrees of what we've gotten when we do the experimental complements as well. So just as a quick summary for part one, what I'm going to mention is that we actually have a material that we believe is a sustainable and low-cost feedstock. I didn't talk too much about the cost of these materials, but we've done some nice techno-economic analysis, which at least on the surface appears to show that they're quite affordable and competitive with some of the petroleum-based counterparts. We have widely tunable TGs. I didn't talk about zero shear viscosities, but again, we can tune that for various applications. One of the nice things is that given the heterogeneity of the bio-based systems, we still have predictable polymerization behavior, and more importantly, predictable property outcomes, meaning that we can actually then say, if you have a pine tree, it's good for this application. If you have an oak tree, it's potentially good for this application. And we also have that versatility in terms of monomers to make various block copolymers. Now, one of the things that I want to mention just before I get to the second part is that we have started a company related to this called Lignolics. So we're unlocking the value of lignin. We have a nice little team at the moment. But the key thing is that we're actually using various feedstocks. So not only wood, but also food waste, agricultural residues, developing some new catalytic processes, and basically not only making things like the adhesives that I've talked about, but also coatings and other additives that are quite useful. Now, one of the nice things here is that we have basically two parties that we can play to. Obviously, the end users that are interested in high performance bio-based materials, but also companies and pulp and paper manufacturers and other companies that are interested in, what do I do with my food waste? What do I do with my wood waste as well? So we interact with the biomass suppliers as well as then partner and with contract manufacturers. So I'll skip through this, but we're just getting started, but we've been able to get a little bit of funding to date. So in the last a little bit, what I want to do is just switch gears slightly and talk about alternatives to BPA from lignin. Now, when we look at a lot of polymers today, I've talked a little bit about polystyrene. I won't talk about PET in this particular talk, but we're looking at lignin as an alternative there. But what I want to focus on for the remainder is looking at alternatives to BPA for things like polycarbonate. Obviously, one of the nice things about all these materials is that when I look at, say, BPA, it imparts rigidity, high TG, relatively cheap monomer, but it's petroleum derived and it has some a very serious potential known health effects. And so we can start looking at all of these. So one example is, in the MacBook that I'm on, Nalgene bottles, etc., the yacht that I'd love to have one day. but also looking at food contact materials and things like dental resins and those sorts of things. So when we think about BPA, there's polycarbonates, epoxies, and other materials, quite a large market, but one of the challenges is the known health effects. Now, there's sort of a little bit of a bad news and worse news that's implicit in this slide, and that's the following. So in about 2012, the European Union and others around the world started banning BPA in food contact materials, and particularly in baby products. Now, there's been a lot of work on BPA-free materials, and one of the reasons for that is because BPA was known to be endocrine disrupting or estrogen mimicking. And so the thought was, if I can make BPA-free materials, they might be better. Now, unfortunately, there's starting to be overwhelming recent work which has shown that many of these BPA-free materials are exactly that. They are BPA free, but they're not endocrine disrupting free or estrogen mimicking free. In fact, some of them are actually quite a bit worse than BPA itself. So one of the things that we wanted to do is we wanted to say, look, can we think about mimicking or making a material that could potentially be better than BPA, or at least better than analogous in terms of thermal and mechanical properties, but potentially better in terms of some of the adverse health impacts. But when we thought about it, we wanted to say, can we do this in a fashion that is at least has the potential to be commercially viable? And the way that we thought about that was, here's in the top in the blue is the industrial process for one industrial process for the synthesis of BPA. Now in the bottom, this is basically a synthesis of our bis-guaiacol F. And so what you can see here is we've got this vanilla alcohol that we get from lignin, the guaiacol we get from lignin. And the key thing that I want to mention is that we use the same solid acid catalyst. So in this case, we can use amberlist 15. We're developing some new catalysts as well. We can do this same temperature, same time. So essentially you can drop this into the same reactor. And now what we start to get out is, instead of BPA, we get out our BGF, where we're missing, for example, the two methyl groups on that methylene bridge. And we have two methoxy groups shown here that are missing in that BPA. So we can take that. I'm not going to go through all the data on this slide. Just suffice to say that we can take this BPA and our BGF materials and different versions of them. We can actually take badge, which is that commercial bisphenol-based material, the epoxy version, so basically a diepoxy, cure it with an MDA, and, for example, make a nice epoxy resin. We can do the same with these top three, which are bio-based materials. This one down here is the commercial analog to BPA, except for you can see that it's missing the two methyl groups on that bridge. But the key point is basically shown over here. So we get similar glass transition temperatures. We get similar moduli, both at 30 degrees, where we want a relatively high modulus. So you can see they're all on the order of 2.5 to 3 gigapascals for both the commercial materials as well as our systems, as well as a little bit softer material that's more easier to process at 200 degrees, where you can see now we're in the about the 20 to 40 megapascal range. So that's quite nice. This is just more data to that effect. I'll skip through that. But one of the things that we wanted to do is we wanted to say, well, can we start estimating toxicity? And so the way we started, and then I'll show you a little bit about where we are with that now, is we use some tools from the EPA, including their EpiSuite tools, to do some estimations. And we could estimate things like octanol water partition coefficients. So you can see things like our octanol water partition coefficients are quite a bit lower relative to BPA for some of our feedstock materials. And also if we look at LC50 and EC50 values. But again, one of the things that I'll mention is these are calculated using the EpiSuite tool, so may or may not be valid. But what we can do is we can actually evaluate our estrogen activity of these BGF materials. And so we do this in collaboration with one of my colleagues, Chang-King Wu, who's in animal and food sciences. And what we can do is we can look at basically estradiol and BPA as our positive controls, and then we can look at several different isomers of our BGF materials as sort of our actual samples that we want to look at. So we can take these materials, we can do a series of assays, so MCF7 proliferation assays and transactivation tests. A lot of data on this slide, but I'm just going to focus on a couple key features. The first thing is that when you look at these tests, one way to think about it is that if I think about that proliferation, anything above 0 is indicative of potential endocrine disruption or estrogen activity, and anything below 0 is effectively considered 0 for these tests. Now, one of the key things that you can see, especially at the higher concentrations, is that many of our materials are actually much less estrogen mimicking than BPA. And so BPA, for example, is shown here in the red. You can still see some that do appear to have some endocrine disruption activity. And one of the things that we've been able to do is actually by separating isomers, actually develop structure property relationships. And with Professor Wu, actually look at how things can fit into the estrogen receptors and really be able to tease out or design these bio-based materials in such a way that they become less estrogen mimicking. And so you can see that at lower concentrations, which would be the typical concentration that I might see in an average human walking around, versus a concentration up here that's that concentration if, for example, I had eaten my Nalgene bottle. So just as a quick summary, we can actually take that, and one of the things that we've learned is that you can see these are all monomethoxy coming from softwood materials. When we actually move to things like dimethoxy, so hardwood type materials, we can really decrease the estrogen activity and still retain a lot of the thermal and mechanical properties that make these materials quite appealing for various epoxy polycarbonate type applications. And so what are we doing with this now is we're actually taking these materials, making things like polyureas, polyurethanes. We're actually taking them, looking at them, for example, as 3D printing materials and 3D printing resins, and also then as dental resins for and food contact materials, in this case, our polycarbonate-based version of these particular systems. So with that, just like to conclude by saying we're really interested in sustainable polymers. One of the things that's key for us is really developing the structure property relationships so we can do the informed depolymerization, the informed design, and actually have some very nice application targets where we can take a holistic view of looking at the feedstock, the potential valorization, some of the health impacts, as well as then the structure property relationships in these. So with that, I'd just like to thank some people, in particular Richard Wohl, who helped us get started in the bio-based materials. Unfortunately, he passed away several years ago, but he was really our inspiration for getting started. Some of the folks on my team that have done a lot of the work that I talked about, we've had a nice collaboration with Rowan. We do a lot of the depolymerization, the catalytic depolymerization in our labs now, and we've gotten fairly good at it. However, the only reason we've gotten good at it is because we've learned a lot from Dion Vlachos and Basu, et cetera. Chris Clockton for help with some of the network materials. Apologies for that. And Chang-King Wu, as I mentioned, from Animal and Food Sciences. These sources of funding, and I'd like to thank you very much and happy to take any questions.
Thank you very much, Thomas. I'll open it up to questions if those of you with a mic and camera want to turn it on. Otherwise, please feel free to type in Q&A and I'll be monitoring that. John, do you want to? You need to turn your mic on if you have a question. John. You're muted, John, I think. Yep.
Yes, this is John Torkelson. Very nice talk, Thomas.
Thank you. Hi, John. How are you?
Very good. So you say that you're interested in structure property relationships. So if we go back to the compounds that you're using sort of as substitutes for styrene in making polystyrene-like materials, those monomers, are huge and have a tremendous amount of steric hindrance, and yet the glass transition temperatures of the polymers you're making are not much higher than that of polystyrene, which based on synthetic materials indicates to me that they have a significantly lower density than polystyrene. So polytert-butylstyrene has a TG that's not much different from polystyrene, but the density is reduced by 10% as a bulk polymer, and that's actually a lot. So have you thought at all about issues like that and where that might provide advantages or disadvantages relative to polystyrene?
Yeah, so yes and no. So great question. So one of the things that we have been able to do, and if I can get this to work in about 5 seconds, I will do it here. So one of the things that we have been able to do, so for example, if you look at the monomethoxy versus dimethoxy, one of the reasons for that huge jump in glass transition temperature is that steric hindrance, which basically the dimethoxy really inhibits the rotation of those monomer units. As far as density, we can think about it in terms of given that we get similar properties at a lower density, and I didn't talk about any of the compression and tensile testing, et cetera, this is a potentially lower weight packaging material, so it could have some advantage also in terms of shipping costs. I think to more answer your question, it does a little bit depend on the various application though. But we do find it interesting that the glass transition temperature is very sensitive. Now, I will mention if we put another methyl group in between the methacrylate and say the phenyl ring, that we see almost no difference between the monomethoxy and the dimethoxy. So it really is that proximity to the backbone that's allowing that steric hindrance to play a role.
Excellent. Thank you. Sunbin.
Yes, hi Thomas, it's wonderful talk. So I'm really glad to hear that you was looking at some of the biological effect of some of the monomer afterward. As an organic chemist, I remember that some of these guaiacol or phenol could get oxidized to quinone, right? And that will also turn into, dark material. And you did mention about the, removing some of the coloring issue in the synthesis. So I have a kind of two related question. Number one, have you looked at the oxidation product of these monomer, when they undergo degradation and how they affect the biology? Like, if you use them for consumer product, how should some of these would cause biological activity, because quinone are known to be oxidizing agent. The other one is about the smell and the coloring. I mean, if I remember guaiacol, they really smell really bad. And so if you have an incomplete polymerization or you have a partial degradation, the polymer will become fairly smelly. And so can you comment about the long-term stability of some of these material?
Yeah, let me handle the second question. Great questions. Let me handle the second one first. So in this particular case, yes, say guaiacol, for example, would have, say, a smell to it. Vanillin, for example, we do a lot of vanillin work in the lab, and so the lab, depending on your overload with vanillin, either smells wonderful or horrible. But the two things to point out, once we actually functionalize these materials, then they do become less volatile. And then also when we do that polymerization, separation of things like guaiacol is actually quite easy in this particular case. So that's just a typical washing step if I want to remove the guaiacol from these materials. In terms of the actual degradation products, great question. I will say that we actually have a grant that is focused on how do we get these materials to degrade better? Because one of the things that I have that I didn't really talk about, but is inspired a little bit by your question, is that these are still methacrylate backbones in the first part of the talk in particular. And so they don't really undergo ready biodegradation, for example, or degradation in the landfill. They're very similar to, say, a methyl methacrylate from that standpoint. So we're actually working on, and we have some promising results, not quite ready to share yet, on basically some catalytic routes to essentially depolymerize these materials so that we can use them again, maybe not for the exact same thing, but use them again. So we haven't, and I don't want to claim that we've exhausted all assays that would need to be done to test the health and safety of these materials. In particular, we just focus primarily on endocrine disruption because that's a known problem for the analogs. So, but yes, there's definitely more work to be done.
Okay, thanks.
Thomas, I'll read a couple from the Q&A, but I had a question in the meantime. First of all, I like that ACS Central Science cover is fantastic. I need to get your artist on that. But I was interested in the switchgrass feedstock variability. I think you said something about different growth conditions or different locations. So that would mean you would get seasonal variability. I just wonder, you talk about, obviously this creates versatility, but is it also a problem in scale up and industrial use eventually, or not? Is it kind of like blending wine in the end or something?
So, perfect analogy. Actually, that's I'm gonna, if you don't mind, I'm actually gonna use that later for the following reason. So when I think about pulp and paper industry, since they make a lot of their money on, or they make all of their money on their wood, they know the composition, they know the growth conditions, and know what they get out every year, every time of year from basically every tree or every plot of land. So information such as the syringol to guaiacol ratio is going to be known, similar to a vintner, for example, knowing you know, the Brix content of every grape in the field. So in that particular case, it is known. Now, one of the things that we are doing in collaboration with one of my newer colleagues, so Marianthi or Patriciu, is actually looking at machine learning approaches so that we can do things like assay S to G content using glass transition and degradation temperature of say the switchgrass sample itself. So we're working on ways that we can do a really quick assay without having to do a GC or proton or a 2D NMR, for example, to get that structure and composition.
Interesting. Yeah, thanks for that. I'll read one of these. Somebody's asked, are the bio-based polymers generally water soluble or even biodegradable? And it goes on to say, imagine if they are water soluble, their use would be perhaps limited. Maybe you could comment on that.
Would be limited, or?
Perhaps limited, yeah, because of their water solubility.
So in general, all of the ones that I talked about today were not water soluble. We can actually make ones that are water soluble. That's actually quite easy to do, either by using some protection chemistries to leave one of the alcohols or one of the hydroxyls, in particular the aliphatic hydroxyl on the available, or also then post-polymerization, for example, with vanillin, we have that aldehyde functional handle that we can use to actually make these water soluble. Reasons that we want to do that are actually looking at lubricant surfactant type applications. But so that also impacts the second part of, or the other part of the question, which is the biodegradability, in the sense that these materials aren't necessarily water soluble, so you don't see very much degradation in terms of at that ester linkage and those sorts of things that you might see for a water soluble polyester.
Yeah. Okay. Thank you very much, Thomas. And I think we're at the time now for your part. I think there are more questions. I think you can go in and look at them.